record, admit. Okay, so in the folder for the week, the one paper you picked up yesterday says like activity series worksheet. Anybody need one? Like not here yesterday? You guys are all here. Okay. So the activity series worksheet that you picked up yesterday, it's got 20 of them on it, and we did like 1, 2, and 3, I guess. But problems 16 through 20, those are the ones that are actually appear 16, 17, 18, 19, and 20. If you do those on this paper, those are the ones that appear on the quick check for you to like predict the products of in case the products actually happen. All right, so we did 1, 2, and 3, and if you did the others, then you can check to see how you did or what you did, and if you didn't do them, you'll see how they go now anyway. So in each of these reactions, you know the reactants, and those two reactants, I got to switch to a different thing here. Those two reactants are either like an element and a compound, and the goal is to look at the single element by itself and figure out what element it would replace and compare the place on the activity series to figure out if the replacement's actually going to happen. All right, so this is the single replacement worksheet. We did 1, 2, and 3. This is number 4. So it's says Cl2, that's chlorine, because chlorine is one of the diatomics. And because it's a diatomic element, it's always going to be Cl2. This is the single element that's by itself. And chlorine's a gas. So in this activity series, it's over here. Like there's chlorine. Now, what would chlorine replace? It's either going to replace potassium or replace iodine. And the element that's similar to chlorine, when I mean similar to it, it's something that's going to be in the same column, is iodine. So the chlorine will, if it's going to replace anything, it's going to replace iodine. And the criteria is, if this element that's by itself is higher on the activity series than the thing it would replace, then the reaction will take place. And chlorine is higher up. So chlorine's above iodine, so chlorine replaces iodine. And it turns out that on the periodic table, in column 17, the elements that are higher up always replace ones that are below. So because chlorine is above iodine on the activity series, the replacement reaction happens. Potassium is all the way over on the left-hand side of the periodic table in group 1. So potassium as an ion has a charge of 1 plus. And chlorine and iodine both have a charge of 1 minus. So when chlorine replaces iodine, you end up with a compound with potassium and chlorine. That's KCl. And then because the iodine gets replaced by chlorine, the iodine goes on its own. And iodine is a diatomic. So it's I2. Potassium chloride, that's the salt that's put into Gatorade. And then you got to put a bunch. Potassium chloride tastes terrible though. So put sugar and some food coloring and artificial flavor or whatever. You got yourself some Gatorade. I don't know if I mentioned this or if you know the story, but Gatorade's called Gatorade because it was invented at University of Miami. The Gators, their sports scientists knew that athletes were becoming fatigued and having muscle cramps because as you sweat out potassium, and the potassium concentration in your body drops down. So whenever you undergo heavy cardiovascular activity, your potassium levels drop. So to replace that, you just make people drink potassium chloride, but the potassium chloride solution tastes terrible, so they put sugar in it, and that's how they invented Gatorade. So Gatorade's actually named for, University of Miami Gators. People drink it all the time. It's good stuff. The G2 and the light Gatorade doesn't have much potassium chloride at all. You're actually kind of just getting watered down Gatorade. But this is one way to make potassium chloride, KCl. All right, this is not a balanced equation though, because the chlorine, there were 2 chlorines on the left, but now only 1 chlorine on the right. So you got to put a 2 in front of that KCl. And there's also 2 iodines on the right, so you got to have a 2 in front of the Ki. Now the equation's balanced. There's 2 of everything on both the sides. Okay, now number 5 is sort of a bit of a trick question. And it has to do with water and the way in which you can write the equation for water. There's actually two different possible outcomes in this problem, but lithium is right here. And then you got H2O. Well, hydrogen is on this list. So let me see if this is on the ion chart. Um, yeah. So the way to think of water is a couple different ways to think of water. Water is both a molecular compound as an oxygen atom with its 6 valence electrons bonded to 2 hydrogens. So that's the way you can think of water as a molecule. So there's O bonded to an H, bonded to another H. That's like the Lewis structure. But water can also be thought of, and it acts like an ionic compound. And on the ion chart, you'll find 2 different ions listed, H plus and OH minus. When water's in water, water is actually, it sounds kind of funny to say, but water in water, some of the water atoms dissociate to make hydrogen and hydroxide. So another way to understand what water is, this is a new thing, is this H2O is the common way we write the formula for water, but you can also think about it as HOH. So it turns out that when metals react with water, it's not that the lithium replaces just the hydrogen and lithium goes with oxygen, but instead the reaction that happens in water with lithium is this lithium would replace the one hydrogen, because hydrogen can have a charge of H plus, and then hydroxide has a charge of OH minus. Now it turns out what makes something an acid or a base is in a solution of water, when there are extra hydrogen atoms, it's an acid. When there are extra hydroxides, it's a base. So water also acts like an ionic compound. So here's what I'm saying. If you see a metal reacting with water, instead of looking at it as Li plus H2O, think about it as Li plus HOH. That's another way to write the formula for water, because water can act both ionically and molecularly. In the case of an ionic compound, you can get a single replacement reaction or a double replacement reaction in solution. So it's not that lithium just goes with oxygen to make like lithium oxide. Instead, the lithium goes with the OH. You need to make a comparison though. Lithium's up here, hydrogen's down there. So what lithium could replace is hydrogen, but not both the H's, just one of the H's. So instead of it being lithium and then hydrogen hydroxide, because that's kind of an alternate way to name water, is like hydrogen hydroxide. Instead, you get lithium hydroxide, and lithium is in the first column of the periodic table, so it has a charge of 1 plus, like it's Li 1 plus, and then it's OH 1 minus. Since lithium and hydroxide is on the ion chart as OH, since lithium and hydroxide each have a charge of 1, it's LiOH. And the other product is because one of the hydrogens gets replaced, so this hydrogen gets displaced, you end up with hydrogen, H2. Now, if lithium and water react, you get a violent reaction and you get an explosion where there's flame. Because in this reaction, not only does lithium react with water to make lithium hydroxide, but you also make hydrogen. And hydrogen gas is highly flammable. And there's a lot of heat that's given off. And oftentimes that hydrogen can ignite. So let me show you some examples of those reactions. You can find lots of them online. Let's see. I got to go get me some YouTube. We used to keep big chunks of lithium and sodium here at school, but then there are these new standards for what chemicals you're supposed to keep in schools. They came and took out all our good stuff. It was such a buzzkill. We had like tons of mercury. We had lots of lead. We had lots of compounds containing like um, cadmium, which is bad. We had chunks of lithium, chunks of sodium. It was pretty excellent. All right, let me switch to this other screen. New share. So if you're remote, this is going to be kind of like choppy and whatnot. But this is a piece of lithium that's stored. I mentioned that the alkali metals are usually stored in oil. So that's a chunk of lithium that's stored in oil. And then the person is going to take it out of the container stored with the oil and slice a little bit off. It turns out the alkali metals are very soft. So although it's a solid chunk of metal, you can just take a knife, take a scalpel, um, a kitchen knife, and cut it. It's kind of like butter, like cold butter. You just slice a piece right off. Now you see that the inside is nice and bright and shiny because the outside has a little bit of lithium oxide from any kind of air that it was in contact with. That's just a conductivity tester to show that it conducts electricity. Like we use that conductivity tester. And then they're going to take a very small piece and drop it in water. And you see as soon as it hits the water, you see bubbling and fizzing, and it's um, it's floating on the water because as the hydrogen is produced, it's like hydrogen gas that pushes it up, but there's hydrogen gas that comes off the top. I don't know if this one's going to ignite, but you can find illustrations of it where it completely ignites. Here they're collecting some hydrogen gas in a test tube. Yeah, so they're collecting hydrogen gas in the test tube. The hydrogen gas is buoyant and pushes the air out, and then they're going to move the test tube over the flame, and it's going to pop. There, like it just blew up. So the little explosion took place. So that's the actual reaction that happens whenever there are. Oh, and they're putting an acid-base indicator in. That's phenolphthalein, because whenever you make the lithium, when you put lithium in water, you make the lithium hydroxide, and lithium hydroxide is a base, and that is phenolphthalein indicator, which turns pink whenever it's in the presence of a base. So this is a confirmation of the reaction. Lithium and water make lithium hydroxide and hydrogen gas. So that's a thing that you need to know, is that when you see these reactions that contain a metal along with a water, and if the reaction takes place, it's a lithium replacing one of the hydrogens, not both of the hydrogens, to make lithium hydroxide and hydrogen. So you may have written that differently. You may have written it as lithium oxide plus hydrogen, and that's not the way it goes. It goes lithium hydroxide. And so another example is that with soda. Oh, this is not balanced then too. So to balance it, let's see. So on this side, there's 2 hydrogens, and on the right, there's 3 hydrogens. So one way to reconcile that is if you put a 2 in front of the LiOH. Now, another way to think of the water is, because water is HOH, there's 2 hydrogens here, and then 2 hydroxides here. Or, in other words, there's 4 hydrogens on the left. I'm sorry, 4 hydrogens on the right, and 2 oxygens on the right. You got to put a 2 in front of the H2O. And now the lithiums are unbalanced too. So it's got to be 2 lithiums and two waters make 2 lithium hydroxides and 1 hydrogen. So number 7 is similar, sodium and water. Sodium is also on the chart up here. Sodium is above hydrogen because it's the hydrogen in the water that gets replaced. So it's a similar reaction. It's NaOH plus H2. Hydrogen is diatomic, so it's got to be H2. And it's 2, 2, and 2. So 2 sodiums, 2 waters make 2 sodium hydroxides and a hydrogen. All right, the copper and iron sulfate. So copper is the element that's by itself. You can find copper on the chart. Copper is down here, down toward the bottom. I put it in green. And the iron is up here. The reaction will only take place if the element that's by itself is above the similar element on the ion chart. And here, copper is not above iron. There's no reaction. And that's because the copper is below iron. Instead, if you were to have iron and copper sulfate, then you do get a reaction. But copper and iron sulfate, no reaction. All right, iron and lead nitrate. So iron's right here, and lead's much further down. Because the iron, as the single element, is above the lead, the iron will replace the lead. Now, which iron it forms is tough to know. There's iron 2 and there's iron 3, and it's not clear in this reaction. So, if you were to happen to know which iron it is, because on the ion chart you'll find there's iron 2 and iron 3, then you can predict which of the products. But there's another way to predict which product takes place. So this reaction does proceed. Let's see, lead, NO3. If you were to say that it's like iron 2, Fe2 plus, and then nitrate is NO3 1 minus. If it's iron 2 with nitrate, then it's FeNO3 2 and lead. If you were to say it's iron 3 plus with nitrate, then it would be FeNO3 3. I'll show you the way in which you predict which of the products it's going to be. But what's more important right now is that you know which or whether or not the reaction takes place and what replaces what. So the iron will replace the lead, and the lead goes on its own because the iron is above the lead on the activity series. So now number 9 is another one of these things where it's something in water. You can think of water as HOH, but when you compare the position of copper and hydrogen, the copper is below hydrogen. So because copper is below hydrogen, there's no replacement reaction. The outside of a penny is made of copper, or like pennies before 1982 were copper. Can you imagine if you had like pennies and they just happen to get wet and a chemical reaction takes place and the penny like makes some kind of solution and the penny goes away? That would be ridiculous. You know, to make a penny, to make a coin out of any metal that's like high on the chart would be stupid. Like if it was lithium, you're like, oh, I got this coin, it's made of lithium. If it ever gets wet, a reaction takes place and huge amounts of heat's made, and I get reactive explosive hydrogen. That'd be insane. It'd be the dumbest thing ever. So coinage metals, people oftentimes call metals that are down here coinage metals. Now we also make coins out of nickel, like so traditionally nickels. There's a couple different reasons why nickels are called nickels, but nickel and zinc are used to make coins, but they're alloys. So whenever you mix metals together, you can end up with properties that are not the same as the single element by itself. But no matter what, because copper is below hydrogen, there's no reaction. I wrote HR. I don't know why I just did that. Because I was looking at the H and HOH. All right, copper and aluminum. So copper is down here, and aluminum is way up here. Copper is below aluminum. There's no reaction. And then aluminum and lead. So we got aluminum is right here, and lead is down there. So the aluminum is above the lead. Because aluminum is above lead, you get a reaction. So aluminum goes with the nitrate. Now, aluminum's easy to know. Aluminum is in group 13 of the periodic table. So Al is always Al3 plus, and nitrate is always NO3 1 minus. So when aluminum goes with nitrate, the formula is Al NO3 3. Because if aluminum's got a charge of 3, and nitrate has a charge of 1 minus, then you need 1 aluminum and 3 nitrates. The other thing you get is lead. This equation is not balanced though, because the nitrates, there's 2 nitrates on the left, but I had 3 nitrates on the right. So to balance the nitrates, you got to have 3 in front of the lead nitrate, 2 in front of the aluminum nitrate, and then because we had 2 aluminums on the right, it's got to be 2 aluminums on the left, and 3 leads on the right. Let me clean that up. 3 leads plus 3 PV. I mean, now in a lot of ways, if you see ideas where there's two chemicals, you can predict whether or not the reaction takes place and predict what the products are going to be and name and write the formulas and get the formulas right. That's the whole plan here. So just comparing the position of the single element on the ion chart to the thing that it could replace tells you whether or not, or on the activity series, tells you not whether or not the reaction actually takes place. So here, no reaction takes place because the copper is below hydrogen, and here copper is below the aluminum. All right, so I'll just do these last three, and then 15, 16, 17, 18, 19, 20. Actually, let's see, 16 through 20 are on the, what do you call it, on the quick check. And that's all you got to do today. So, okay, Cl2 and NaI. So you got chlorine, and what chlorine could replace is iodine, and chlorine is above iodine. So if chlorine reacts with sodium iodide, then the chlorine replaces the iodine. Sodium has a charge of 1 plus, and chlorine has a charge of 1 minus. So the compound that would be formed between sodium and chlorine is NaCl. And then you also get just the iodine goes by itself. But iodine is diatomic, so that's got to be I2. And to balance the equation, you need a 2 in front of both the sodium compounds. So you end up with 2 of everything. And then 13, you got iron, and this is silver acetate. This C2H3O2 that you find on the periodic table as the acetate anion, when that's with hydrogen, that makes vinegar. So, but here we got iron and silver. So we're going to compare iron and silver. Iron is here and silver is down there. It's always whichever element's by itself. If that's above the element it would replace, then the reaction takes place. Iron is the single element and it's above silver, so you get a reaction. And if it's iron 2 is the most common. So if you have iron 2 and then C2H3O2 is acetate, C2H3O2 has a charge of 1 minus, you're going to need 2 acetates for every iron. It turns out silver is always 1. So that's why there's only 1 of each, because it was Ag1 plus. But this is going to be Fe and then C2H3O2, 2 of them, plus the silver. Let me just move this thing. It was Fe2 plus and C2H3O2. That looks better. Because there's 2 acetates on the right, you got to put a 2 in front of the iron, acetate, and that makes the irons wrong. So you got to have a 2 in front of the iron. Oh, wait, not that way. I don't even know why I did that. You got 2 iron acetates on the right. So you got 2 acetates on the right. You need 2 of these acetates on the left. So 2's got to go in front of the silver acetate and a 2 in front of the silver. Now you got 1 iron on both sides, 2 silvers on both sides, and 2 acetates on both sides. And then 14, aluminum with copper chloride. This is similar. You did zinc and copper chloride, and zinc and copper chloride worked because in the lab, zinc was up here and copper was down there. So you put a piece of zinc in with copper chloride and the zinc replaced the copper. You could do exactly the same thing with aluminum. Aluminum is also above copper. So because aluminum is above copper on the activity series, you get a reaction. And aluminum is Al3 plus and chloride is Cl1 minus. Aluminum is 3 plus because it's in the 13th column of the periodic table. Chlorine is 1 minus because it's in the 17th column of the periodic table. So when aluminum and chlorine get together, it makes aluminum chloride, it's AlCl3, and then copper is monatomic, it's just a Cu. And the chlorines are not balanced, so you got to put a 3 in front of the copper and a 2 in front of the aluminum chloride, and that messes the aluminums and the copper up. So you're going to need 3 coppers and 2 aluminums. So it goes 2 aluminums and 3 copper chlorides. We're going to make 2 aluminum chlorides and 3 coppers. Those are going to be the ratios of the elements in the compounds when the reaction take place. If you were to react like 1 atom of aluminum with 3 copper chlorides, nothing happens. You have to have the ratio of 2 aluminums to 3 copper chlorides in order to consume everything. And then you end up with exactly 2 aluminum chlorides and 3 coppers. We're gonna use this to figure out like masses of the stuff. So if you wanted to react like 20 grams of aluminum, you could figure out how many grams worth of copper chloride you'd have to have in order to make all the reaction proceed. Like what's the, not just the relative numbers of them, but the relative masses of the compounds. We'll do that. Okay, so those are a good review of like the process. That's pretty much it. The only new trick, the new thing I showed you about today, is that in single replacement reactions, like in numbers 9 and 11, or wait, number 9, number 5, 7, and 9, in each of those, when you see a metal reacting with water, it's not that it's H2O, but HOH, hydrogen and the hydroxide. Water is by far the most unusual substance known to man in so many different ways. We call it the universal solvent because it's it's water, so it's the basis for everything that's aqueous, but it can also be a solvent for organics or non-polar substances. It acts like a molecule. It acts like it's ionic. The components, hydrogen and hydroxide, are the 2 major components of either acids or bases. So when hydrogen and hydroxide are in equal concentration, it's neutral, and we say that that's like pH balanced. If there's extra hydrogens, then it's an acid. If there's extra hydroxides, it's a base. So everything that makes things acids or base has to be solutions in water anyway. And water has very unusual physical properties. For all substances, if you like change a liquid into a solid, the solid's more dense than the liquid, except for water. That when ice floats on top of water is a complete freak show of a physical phenomena. For all other substances, if you take the liquid and you freeze it, it makes a solid that's more dense and it'll sink. If you were to take like an alcohol and freeze it, it's more dense and it sinks to the bottom. All other substances, when the liquid freezes, it sinks to the bottom. Ice, it floats. That's ridiculous. And when I say the only substance out of like hundreds of millions of substances known to man, it's the one. It's a nutcase freak show chemical. But it's so ubiquitous and important in our life that we just think about it as the most boring chemical. But in fact, water is really, really exciting. If you get excited about a chemical, getting excited about water is a good one. So that's a thing to know that makes water peculiar in these reactions as ions is right as HOH. So like we named it as an ionic compound or as a covalent compound. As a covalent compound, we named it, you can name it dihydrogen monoxide because it's 2 hydrogens and 1 oxygen. But when you think of water as HOH, as this compound, it's also hydrogen hydroxide. Those are the like 2 chemical names for it. It can also be called hydrous acid. You can give it a bunch of different names depending upon the way in which you're dealing with it as a chemical. But in single replacement reactions, hydrogen hydroxide is the way to go. All right, you can do the quick check on your Chromebook if you want, but make sure you have like 15, 16, 17, or 15 through 20 done, and the problem 16 through 20 are the ones that are in the quick check. And that's all you got to do for today and this week. We're going to look at other types of reactions next week, like double replacement reactions, combustion reactions, properties of synthesis and decomposition reactions. predicting whether or not synthesis reactions happen or decomposition reactions have other tricks. So there's different methods to figure out, like, are reactions going to take place and what the products are going to be. Let me find the updates. Yeah, so it says single displacement, because you can call a single displacement or single replacement either way. In the single replacement quick check, there are like 11 questions. Some of them just are about balancing or determining whether or not reactions take place. And then the last one, write the balanced equation for the products. And that's numbers, this is like 16, let's see. Yeah, number 2 is like actually number 16, 17, 18, 19, and then 20 on the worksheet is the remainder of the problems. I can't look up there, that's all slow. All right, that's better. We're like zooming. This is like the zoom of this, if that makes sense. So if I watch that and run the mouse, that's behind because it's going from this computer out to the interwebs and then coming back to that one, which is insane. But it made it work.